In this video, we'll introduce the concept of undersampling, which is also known as aliasing. We learned previously that when you're sampling a signal, you start with a continuous time signal at some frequency, and then you take samples at a certain rate, and what you're left with is a discrete time signal. If you've done your sampling properly, it'll be possible to take the list of samples that you generate and to recreate the original signal. So for example, if you had some signal that looked like this, and then you took enough samples, then if I got rid of the red signal and just saved the list of blue samples, the idea is that you'd be able to connect the dots or somehow work backwards from your blue samples to get the red signal back. If you've taken enough samples, it should work. However, if you haven't taken enough samples, then you will have undersampled. And undersampling simply means that there's not enough samples for you to accurately reconstruct the continuous time signal that you started with. In all cases, we're going to start by understanding how this works with cosines, and then once we understand how this works with cosines, we can extrapolate from there onto more sophisticated signals. So if you remember, we started with a continuous time signal x of t, which was, as always, expressed as 2 pi ft. And after we sampled it, we wound up with x of n, which was cosine of omega n, where that capital omega is the discrete time frequency in units of radians per sample. And again, the idea is that I should be able to give you the list of samples x of n and also tell you the sampling frequency, and you should be able to work your way backwards to determine the original red signal, the continuous time signal that we started with. So let's do an example. Suppose we have a continuous time cosine at 30 hertz, and my plan is to sample it at 90 samples per second. So let's see what I think I should get. So if I do this, I'm expecting a discrete time frequency of 2 pi times 30 over 90, which is going to give me 2 pi over 3, which means I'm going to expect a discrete time period of 3 samples. Let's give that a shot. So let's actually try this out and see what we get. So n cosine of 2 pi over 3 times n, 0, 1, 2, 3, 4. And if you go and you plug these into a calculator, you can work out pretty straightforward that the values you get are 1, negative a half, negative a half, 1, negative a half, and so on. And if you look carefully, you can see that the signal repeats every 1, 2, 3, and then it starts again. 1, 2, 3, and so on. Okay? So this definitely has a period of 3 samples, which is what we expected. So that's good. Now, suppose we're working backwards. Suppose I just give you this list of samples, and suppose I tell you that your sampling frequency was 90 hertz. Do you have enough information here to work backwards and determine that your originating cosine was 30 hertz? Well, let's try that. We can see by observation that the period is 3 samples. So therefore, we know that our discrete time frequency has to be 2 pi over 3. Again, that we get the 3 by observation. We can set that equal to 2 pi times the unknown f, which is what we're trying to work backwards toward, divided by the given sampling frequency. And there's not much math left to be done there. We can work backwards to see that our original cosine frequency was 30 hertz. And because we were able to get our 30 hertz back, that means we did take enough samples in this case. So this worked. Now let's look at what happens in a different case. Let's try one where it doesn't work. So let's keep the sampling frequency at 90 hertz, but instead what we're going to do is we're going to try digitizing a 60 hertz cosine. Okay? So same samples, same sampling frequency rather, different higher frequency cosine. So let's see what happens. So in this case, what I'm expecting is an omega, which is 2 pi times 60 over 90, which works out to 4 pi over 3. Or if you like, we might expect that to be 2 pi over 1.5. So we're expecting a period of 1.5 samples per period. So let's give it a shot. N cosine of 4/3 pi n. And once again, we can go plug these values into a calculator. And what we see is that we get 1, -1/2, -1/2, 1, -1/2. That's just what you get when you plug it in. Now this is interesting. What we've just discovered is that the list of samples we get when omega is 4/3 pi is exactly the same list of samples we get when omega is 2/3 pi. So in other words, we've just demonstrated that cosine of 2/3 pi n is the same as cosine of 4/3 pi n. Okay, if you look at the two sets of samples, they're exactly the same. That's kind of weird. So, what does this mean? Well, for starters, it means that we can't work our way back to the 60 Hertz signal anymore. Let me be specific. So, suppose I gave you just the list of samples, 1, -1/2, -1/2, 1, -1/2, -1/2, and so on. And I told you that it was sampled at 90 Hertz. So if I gave you those numbers, you would look at the numbers and you would say, oh, I observe a period of 3 samples, which means that my discrete time frequency must be 2/3 pi. And because I know that because I'm given that my sampling frequency was 90 Hertz, I'm forced to conclude that what I originated with was a 30 Hertz signal. But that's not the case. We know that in this case, we started with a 60 Hertz signal. So why was I not able to retrieve my 60 Hertz signal? I was not able to retrieve my 60 Hertz signal because I didn't take enough samples. My sampling frequency was too low. Okay, my f sub s was too low. And as a consequence, instead of being able to retrieve the correct 60 Hertz cosine that I started with, instead I retrieved an aliased frequency. Instead I retrieved a 30 Hertz frequency, which is just incorrect. So that's an example of what happens when we don't take enough samples. Now let's look at an example that would try. Let's actually plot this rather. Let's plot this and see if we can determine exactly what happened. So what you're looking at here is the 30 Hertz cosine, and I'm sampling it at 90 Hertz. So if the cosine itself has a frequency of 30 Hertz, I sample it at 90 Hertz, 3 times that, I should expect 3 samples per period, and that's exactly what I observe. Right, I get 1, 2, 3, and then the next cycle has 1, 2, 3, and so on. Okay? So that all makes sense. So now what I'm going to do is I'm going to superimpose on top of this the 60 Hertz signal. So the 60 Hertz signal is now shown in orange, and you can tell that it's 60 Hertz because you get 2 cycles of the orange signal for every 1 cycle of the blue signal, so it's double the frequency, it's double 30 Hertz. And what you can see is that the dots still represent samples that occur at 90 Hertz, right? I haven't changed the samples at all, okay? So what you're seeing is that I've taken the orange signal, I've sampled it at 90 Hertz, but just by observation you can see that I haven't taken enough samples to be able to successfully rebuild the orange 60 Hertz cosine from those samples, right? If all I did was show you those samples and say rebuild me the cosine that these came from, the most logical mathematical answer would be the 30 Hertz signal, right? There would be in fact no way of knowing that what I had meant was the 60 Hertz signal. And the reason that is because I didn't take enough samples. If I want to be able to accurately reconstruct the 60 Hertz signal, I need to take more samples. Knowing how many samples to take will be the subject of the next video.